right, I'm recording. Let's stop that. Great. Oh, are we good to start then? Can you hear me okay on there? Great.
Hi guys, I'm sorry I cannot hear you. Are you talking?
Yes, I'm talking. Can you hear me? I've got audio confirmed from Kevin. Anyone else having problems hearing me? I can talk louder too if needed.
Yeah, I can hear you now. Thank you.
Awesome.
Did you Slack on engineers?
Yes.
Okay, perfect. Thank you.
I'm gonna mute my Slack notifications so I don't keep getting pinged. All right. Okay, great. We good to go? All right, so my name is Skylar Murray. I'm an engineer here at Allrecipes Meredith. I've been here about 2.5 years. And today I get to talk about one of my favorite things, genetic algorithms, machine learning. I did some research on this as part of school, and I was excited to explain a little bit today and cover a couple different scenarios where this is useful, including music, games, and I want to talk a little bit about websites as well to see where this might actually be applied in the work environment today. So genetic algorithms, oh, come on, go over, there we go. I wanted to jump to this real quick. So this is a quick, can you guys see this on the screen? Oh, it's not, this is wrong. Is this on the stream? No, on the stream, on Zoom.
See it.
You can see it? That's Victoria.
Victoria, you can see the website up there? Okay, so this is a funny little program. It's using a genetic algorithm to figure out an optimal design for a car to drive over this terrain. And so what you'll see is it follows the current leader, at least the one that gets farthest in each generation. So each time it resets and generates, it's creating a new generation of individuals with different genetic sequences, essentially, depicting what type of tire, how fast the tires spin, and also the body configuration, where the tires exist on the body. And it just runs through this over and over again to try and converge to a solution that's going to get these cars as far as possible. Of course, the terrain gets more bumpy the longer it goes. And so most of the time, they don't get much farther than about, I think the best one I saw was around 150 when I was playing around with this last night. But as you can see, it kind of converges a little bit to these cars that have, okay, 2 wheels with a decent base and some matter stability. But it's, I don't know, even with this, they kind of can get stuck in these little local minima where they just can't get past it. And this is kind of an interesting view of what you can do with a genetic algorithm. This isn't maybe necessarily applicable. I'm sure car designers today aren't using genetic algorithms to design their cars, but there's a number of interesting applications that you can use these for. I'm going to go over a quick view of what a genetic algorithm is and how they can be applied. So they are essentially optimization algorithms trying to find an optimal solution. There's a lot of different approaches to optimizing problems, whether it's like hill climbing or, let's see, there's simulated annealing, and there's a whole host of optimization algorithms out there. This one is genetic algorithms tend to be good at exploring multidimensional spaces, and also ability to achieve unique results that a human might not be able to come up with on their own because of the way that they function. And they don't need technically a specific knowledge of the problem area. You just have to define a fitness function that will evaluate the fitness. But unfortunately, because of the way that they work, it can take a long time to converge to a good solution. And they may or may not actually find the most optimal solution, but they'll probably find a pretty good one. But even then, they're still subject to what a lot of optimization algorithms run into, is they can get stuck in local minimums, or which is a big problem with any optimization algorithm. And there's different ways to combat that. Some real world applications that these have been used for. There was a space antenna designed here. You can see in the lower left. This was designed and put on a satellite to optimize for a couple of contrasting design requirements that they couldn't necessarily come up with the right solution, the engineers themselves, and so they wrote this algorithm that produced this funky little antenna, but actually ended up performing well enough to reach the requirements they had. I was reading, there's other things about aerodynamic optimization of a hypersonic reentry vehicle, of designing the shape and fin location and things for a vehicle coming back from space and how it would function in with the heat waves and everything. And that was an application used to take a genetic algorithm and apply it to that situation. This figure on the right is kind of interesting. It's called muscle motion-based movement. And I'm going to show you a little video from this. I got to find the right tab here. So this is a study done on trying to build something that would mimic correct muscle motion and how to figure out how to make things walk without actually teaching them. And so they put, can't see that full screen. There we go. So they put these models that had muscles and muscle decay, and they're trying to simulate that. And then they use this optimization with genetic algorithms to teach them how to walk, essentially. And with no other input than just how far can they get in this environment, they kind of figure out how to do it. So you can kind of see the first generation falls over really fast, 6th generation, 17 generations in, it does okay, but finally at about 900, it's doing really well. You see the same with a different body type, different muscle structure. These are all using basically genetic algorithms, say how far can this thing walk. And the one side, it kind of goes off the wrong direction. Yeah. Well, Jen, we're going to get there. I'm kind of doing a rough overview of them first, and then we'll dive into the nitty-gritty details of how they actually work and what the purpose of genetic is. And then I'll only show maybe another minute of this, talking about targeting different speeds and actually be able to converge on somewhat like naturally looking gaits. And they're not teaching it how to walk. They're just saying, hey, if we're targeting this type of speed for forward movement, how would you actually move and how would you actually walk? I think this one was kind of interesting where it optimized to, it's better to jump at 2 meters a second than to actually like walk quickly at 2 meters a second with this current body type and muscle structure. So these almost look like how an animal would actually move in real life. And it's kind of interesting to see how that works. And then they throw things at them too, like how well can it handle random perturbations on it. But I watched this whole thing's 5 minutes long. I won't make you watch all of it, but it's kind of fun to look at some actual applications. Now, getting into how this algorithm actually works, built off of kind of 5 steps. You have an initialization phase where you create all your individuals in the population. So those are, for our car example, you have some representation of an object that is represented. Okay, here's the different body types, and they usually have either bits or real numbered values that they can flip to determine what the actual setup is. You have different bits say, oh, this is in that car example, this is a rubber tire versus a bicycle tire versus a hard tire, and then different lengths on how far apart the wheels are based. You all to do that in your initialization phase, get an initial population, and then you have to assign a fitness to that. And a fitness is some sort of function, a deterministic function that you give an individual, and it basically determines how good of an individual this provides. So in our example with these animals that are trying to walk, it was basically how far could those progress before falling over, and you get a better score the farther you got. Or in the same with the car example, how far along it got in that environment is how high its fitness would be. And then from there, depending on the parameters you've given to your algorithm, you do a selection process. and say, okay, I'm going to select the n best individuals. You do add some kind of randomness to that to take a sampling of the entire population, and there's different selection pressure parameters you can do too that says, hey, I want to skew towards selecting more of the better performing ones. And then from there, you take those individuals, you do crossover, which is you basically breed the two individuals, and so their genetic makeup is combined in I guess the normal term is stochastic, which basically just means random, but the proper term is stochastic. And so you combine them in a stochastic way to create new individuals, and then potentially doing some mutation, and you have a certain mutation rate, which is say, oh, I'm going to randomly flip this bit on each individual or a different bit on each one. And then you do the whole thing over again. So you have a new population, you figure out their fitness, and you go through the whole process again. And then you have a stopping criteria that you check after each iteration that says, hey, once I have individuals that are good enough to solve my problem, then I'm going to stop. And then I have my solution, and I can apply it, whether it's a car that drives really far, or an animal here that we saw that was walking a great distance without falling over, or our antenna that we need to talk with a satellite in space. So fitness functions are usually assigning a real number value. Usually it's ranged between like 0 and 1, higher is usually better, and it evaluates how well an individual is performing in that space. We talked a little bit about that. And then selection, choose the best individuals. There's a model called elitism that says, hey, I'm always going to preserve the best individual so that that good genetic material persists in the environment and produces more offspring in the future. And so that way it kind of helps you from necessarily falling away from, oh, we had a good model, but then we didn't preserve it for the next generation, and it's the random mutations got us even into a worse situation. So, and then there's crossover. Here's kind of a simple example of what an individual could be. Say these bits here represent, the first column says, okay, I have, like with our car example, say the first column says, okay, if it's a 1, then I have road tires. If it's 0, then I have bicycle tires. The next individual's gene could be, oh, I'm going to be a square, or I'm going to be oblong, and so on and so on. And so each one of these bits would represent a different trait that would be expressed by the individual. And crossover happens, you take 2 individuals, and then you can see it makes offspring with genetic material from the parent, the colors denoting which individual you receive that from. And mutation is a way that you combat low diversity in populations. So if you are kind of converging to a local minimum without mutation, then with mutation, you'd be able to kind of get out of that minimum and get into a new search space that help you hopefully get to a more optimal solution. And so here it's saying, okay, usually the rate of mutation is kind of 1 over n, where n is the number of traits. And so each individual offspring member usually has 1 trait that'll be flipped and produce that. So let's get into some of the fun applications for this. There's a number of people have done work on algorithmically composed music using genetic algorithms, kind of a way of assigning, like making music with this. I'm going to show you a fun game that was made for to use genetic algorithms, and I want to talk maybe open it up to a little bit about talking about website design with genetic algorithms and how that could possibly apply. Music is interesting because it's a unique domain, and like think about how would you actually write a fitness function for music. So I actually did research on this in school. Wrote my thesis on this. On developing a program to do this exact thing, and that was a hard question for me to figure out how to exactly do that. And so I kind of did what most good researchers did, and I really limited my scope. So I limited my research to melodies that were all the same rhythmically, so just 8th notes, and talking about feature selectors. We'll get into how you actually rate a piece of music in a fitness function. But what I did is I made a row of collection of feature selectors. I said, okay, I want to look at the shape of the melody. Is it flat, roughly? Is it a rising melody, a falling melody? Is it going a big arc? Does it fall down into a bottom arc? Looking at how linear the piece of music is. Does it have a lot of random jumps and changes of direction or not? What's the key of the music? What types of intervals are in there? What's interval prevalence? And so I built a bunch of these little what I called like mini fitness functions. I said, okay, I'm going to rate this melody for its shape, and then I'm going to rate it for its linearity. I'll rate it for the key that it's playing in. I'll rate it for all these different things. And then I actually built a what's called a meta fitness function, where I took all those scores, gave them different weights, and produced a final fitness for a piece of music. And so what you'd get, if you look at this little grid here, these are the different weights given to each one, plus the target score I had for each one. And so it would reward melodies that converge towards that target score, and it would like penalize ones that were farther away from that target score. And so eventually, following these weights and targets, you would get something that looks like this. So it's in the key of G major for the most part, except for the fourth measure. Those two, or I guess the A sharp in there is not in the key of G major, but it's kind of a top arc melody. It has a little bit of jumping around, but not a lot. And it's this rising and falling melody. Using different parameters. This is actually generated by a genetic algorithm. This next one was a different set of weights that wanted a different key, and it wanted a different melody shape and different amounts of linearity. So you see the more angular jumps in here a little bit. And this is a way of kind of generating genetic music through this. And you're not necessarily assigning like a fitness as far as like how good of a piece of music is, but in this you're saying, okay, how well does it fit these parameters that I've set up to follow? Does that answer your question, Ed? Ed was asking, how do you put a fitness function on a piece of music? So, okay. Thanks. Yeah. Yeah, and that's another interesting thing to ask. Kevin mentioned it sounds as good as it sounds good to the computer. That's one of the kind of bottlenecks with some people's implementations of genetic algorithms is they use what's called human in the loop, where the computer produces something, but then a human has to go and listen to it or look at it and then assign a rating to it. And that's going to slow your generation down extremely because you have to wait on a person. Music is very linear, and so the person usually has to listen to it in real time. Whereas if you can build a fitness function that's based off of pure analytics that can quickly analyze a piece of music without having to consume it in real time, then you can get your generation and your convergence to happen a lot faster. Question in the back from Briar. I don't have samples of these. I have to go dig in my research to get some of these out. But if you want to ask me later, I'm sorry, they're asking if you can hear the music. I don't have samples currently, but I can provide those later if there's some requests for it.
Do you remember listening to it?
Yeah.
And how they strike it? How they strike it?
They're asking me to hum it, but I think I'm going to save you guys that.
Well, do you remember if you liked it?
I was actually, David asked if I liked these melodies. It was actually interesting to see them converge the different properties. Honestly, I spent hours just like playing around with my weights and measures to see what I could get out of it. Like even going back to these linear examples, like having it produce something that's extremely like discordant and jumping around a lot versus a nice rising and falling melody. It's kind of fun to see you build something and see it come out, and actually to have it converge and say, hey, I only want things in G major, and then, hey, it produces stuff in G major. Or I want things with a lot of intervals of the fifth inside the melody, and so it would optimize for that, and you would see a lot of those happening inside the piece of music. And so it's fun to get one of these things together and working, especially in a domain that is really consumable, as opposed to like, oh, here's a car, it's driving across. It's kind of neat, but like music, I feel like has a lot more kind of pathos in it and really affects people. And so this was part of why I wanted to go into this. So. Question from Ryan.
So for music, for creating music, how is this better than generating given single parameters? So instead of working up to where you want it, why not generate within?
So Ryan is asking for music, instead of starting from kind of a random initialization and then working towards a final result, he's asking why not just generate music given a certain set of parameters. That you could do that, that's a different approach to generating music. So genetic algorithm is more of, hey, let's given an individual, let's morph it and breed it until it produces the final result. Whereas you're saying, hey, I actually just want to produce something. There's actually some work by a guy that did something like that, where he basically built a system that would produce music. It would consume, say you gave it Bach and said, hey, consume all this Bach music, and then it would produce music in the form of Bach that was good enough to confuse musicologists and say, hey, this looks like Bach wrote this. Or even like Beethoven, and he actually has recorded CDs of performances of his music that are pieces of music that sound exactly like Beethoven or Rachmaninoff. And someone who knew those composers would be like, oh, I've never heard this piece before. This sounds just like Rachmaninoff. And they wouldn't know that it was generated by a computer. It was that good. So that kind of work is possible, right? It's been done. Any other questions? Okay. So talked about melodies. Okay, games. There's a game out there called Darwin's Demons. And I want to show it to you. I'm going to figure out the best way to do this. Let's go to duplicate so I can actually see the screen. Tell me if this ever jumps off the Zoom.
Right.
Not showing on Zoom? Okay, I'll have to move this. I'll have to change it to desktop one. Okay, can you see this? No? Okay, we'll change Zoom then. Screen controls, share screen. I'll show screen. All right, can you see screen? But when I go to this, you don't see it? Okay, so this is a game some students at University of Idaho built. And it looks like your basic Space Invaders game. I mean, you fly around, you shoot stuff. I don't know if I'm gonna get in trouble for playing games at work, but what's happening here though, besides me dying, is this is actually a game built on genetic algorithms. And so each one of these enemies here is trying to kill me, and it's being rated each time on how well it does it. So it's rating, okay, how long does it last? Does it get shots at me? Okay, so it actually killed me. But what happens is each time you either, I mean, I lost, but each time you beat a level, it has a generation, and it's gonna look at how well, does it have shields? What kind of dominance level of this enemy is there? Its relative fitness for aggression, accuracy, and lifetime. So each enemy is rated on how well it does, how aggressive it is, by how far it moves down quickly, how accurate it is with firing, and then how long it actually survives on the screen before you kill it. And so there's also things for, okay, how fast does it fire? And how fast are the projectiles that it fires? Does it avoid you or does it follow you when you're flying around the screen? What does the enemy do? Does it charge down or does it retreat? These are all different elements of the enemies that exist. And so each time you beat a generation, essentially, it takes the most effective enemies and it breeds them and creates new one. It does some mutation too, so you see different stuff show up. And then you get to face those new enemies the next time. And so you do this successfully, and eventually the game figures out how to beat you. And so with this game, there's a whole bunch of different like weapons layouts and ship layouts and special abilities and things. But no matter what you do, even if you cheat and give yourself like unlimited money to keep upgrading yourself, eventually the game figures out what enemy is going to beat you and kill you. And so it just does that through natural selection pressure. And there's a YouTube guy called Scott Manley that does a video on this. Does a little more in detail, but he kind of shows like, yeah, I know he survived to like generation 7 or 8, but then if you cheat, he got up to generation like 69. He had this amazing ship with homing missiles and lots of stuff, but like the enemies eventually got too hard, even if you were cheating, that the game was able to beat you because it figures out, okay, this is most effective against your current play style, your speed you're moving around the map, the current weapons you have, and the enemies figure out to avoid you and to stay away from you, but then keep firing. And so it's kind of a fun little application for this kind of algorithm. So question from Philip. On the same layout, or? So Philip was asking if someone plays a game and then they get beat, and then another player comes in on the same setup, essentially, session, and starts playing, how well do they do comparatively? I don't know if they've done that testing, but it'd be interesting to try out. Or to be like, hey, we're going to trade spots every like 3 generations to kind of throw the algorithm off to see what happens.
Every time it dies.
Well, yeah, you could reverse like the process and say, okay, you fight against the enemies, and we'll just. Yeah. Yeah. So you could flip it around and turn the player into a genetic algorithm, and then you should have a computer could fight itself essentially.
Yeah. Figure out how to better.
But then the enemies would get better and better as well. So, but yeah, I thought this was a fun little application. I mean, the game was built by students, so it's not a AAA rated game, but it's actually a really interesting way to kind of explore a genetic algorithm and how it can work and the power that it can have in solving a problem, whether it's an optimization problem, or here the optimization is how do I kill the player. So let's go back to this. So that's Darwin's Demons. I wasn't able to build out this as much for websites, but you can imagine if we look at like the All Recipes website. If I can type, computer's slowing down. I should probably close this. We're just showcasing our wonderful page all the time here, as Ed comments on. Yeah, no, I think my computer's hogged down by something. Yeah, Ed was. Yeah, I was talking about you could use genetic algorithms to power a taste profile. And Justin mentioned like website design might be interesting. If you, one thing I was thinking, like, hey, even if we took like the top 4 things we show on our homepage feed, I mean, maybe it's better to actually have like a real video card here, or maybe it's better to have an article card or different things. And you could, instead of, I mean, I know our editors work very long and hard to decide what content to feature on the site, and we do have paid promotions. But you could imagine saying, hey, we're not sure what the best thing is, but hey, let's design an algorithm that says, hey, we're gonna put our options are a video card, an article card, a recipe card, and we're gonna feed it this essentially population of cards, and then let a genetic algorithm figure out what the best 4 cards are to do that. And so each time a user goes to the site, it would get a specific individual that expresses its genes in a way that shows, hey, first I'm going to show a video card, then 2 recipe cards, and then an article. And if a user ends up clicking on that, then that's a positive reinforcement for that individual. And then with the amount of users we have on the site, you actually would probably get a decent amount of input on how well an individual is doing. And so eventually you could just go through the whole thing. Okay, what's your fitness function? Say we run it for 4 hours, and then we take the fitness after 4 hours to see who did the best, and then we crossbreed, crossover mutations, and then keep going to converge on what is a better layout for the first 4 cards on the site. If you want to get more crazy, you could say, hey, maybe we want to make our RDP page modular, and we're not sure what the best layout is for it. So we're going to build these small building blocks and let a genetic algorithm figure that out for us. Maybe it's better if the image is on the left instead of the right, or maybe this is the wrong text style. Or I know we do a lot of A/B testing, but this would be kind of automatic, and you give it a realm to play in, and you could actually convert to something very interesting, especially on high traffic pages that are producing a lot of traffic. You could do it to kind of converge on something that's a little more optimal. So that's kind of, I think that's one of the things to be most interesting. It's definitely an engineering challenge, to do something like that, because you need to have good reporting, make sure that clicks are being registered to get that feedback and figure out the fitness of a certain individual. But you could definitely look at a way of applying this into website design, content design, what content you want to show on a page, what image you want to show on a page, colors, different things like that. So I think there's a lot of potential for that, not just in building games or writing cool music, but even in doing work and finding out what's best for a user. So that's about all I have to present today. I hope you guys have enjoyed it. If you have any questions, please reach out now or later on. Okay. Got a question from Phil. Genetic? Did I not answer that?
I mean, basically, like I said, learning is done.
Yeah, so the genetic part, as Philip was asking, what does genetic mean? It's because you are building this expression of an individual that's expressed by genes, and the genetic part of this algorithm is that you're essentially like trying to breed an optimal solution. And so each time you go through, you rate someone's fitness, and it either lives or it either dies or it produces offspring, and those offspring will carry the traits of its progenitors, and then those will hopefully help it converge to an optimal solution. And that's by finding the best expression of those genes, whether it's a web page layout, whether it's the design of a tire in a car or an antenna or a monster trying to kill you in a video game.
How many offspring?
Yeah, usually, so Kevin was asking how many offspring are produced as part of a genetic algorithm. That's one of the things too with like optimization algorithms, is figuring out the parameters that they will live inside of. For this type of problem, it depends on like the problem space you're doing in. In the car example, they had 20 individuals in a generation, and then usually what happens, you have some sort of selection amount where you say, okay, I'm going to select the top 50% individuals, and then those ones will crossbreed to create new individuals for the next generation. And so usually you have a set number of individuals you will have in a generation. And I mean, maybe you only pick the top 25%, but then you can have problems if you only select the most performant ones. They may also converge quickly to a local minimum that you don't actually want to get to. You had a second question, or? Okay, Kevin was asking about the Cognitive Services API that Microsoft puts out through Azure. We did a hackathon here in All Recipes for it last year, and wondering if there's any commercial solutions using genetic algorithms. I don't think they have one in their solution. They may have it in the machine learning playbook that they have, where you can go and play around with a little bit. There is, I think, he's asking about the reason behind that. I think the cognitive services skewed a little more towards towards like neural nets and computer vision solutions, and a little bit and natural language processing, and which are kind of keyed on different problem sets. Genetic algorithms are kind of, I feel like, I mean, I studied these in college, and so it's just kind of funny because I feel like I kind of went to a niche that didn't get used as much in today's world, because everyone's about deep learning. Like we look at AlphaGo that Michael Hixenbot presented about a little while ago, and playing Go, and it's maybe a little bit out of vogue, you could say, but there's still definitely applications for it. I think there's even a Wikipedia page on applications for genetic algorithms, and I think in the either 80s or 90s, I think IBM had a solution that they put out. This is coming off their Wikipedia page. So, I mean, it's probably less well known in some scenarios, but it's been used in producing specific products like those ones I mentioned. So.
seems like the initialization is pretty tightly coupled to whatever domain you're working on. If you're working on music, your initialization phase is pretty specific music, like number of large intervals, things like that. Whereas a website design might have to be the color of that side of the screen. So maybe that's why too, is because it's such a fuzzy thing. The initialization part is pretty dependent on certain static things that you want to test out. So that's pretty frequent.
Yeah, Justin was mentioning here that the kind of the space that genetic algorithms work in, you have to figure out a way to express the genes that you're trying to do. Whether in music, it's your notes and the notes intervals, whereas in the website design, you have to figure out, okay, what are the genes that we want to express, whether it's a color or a type, or if just we want this type of block in there, this content block or this content piece. So there's definitely a startup cost to getting it into a genetic algorithm, to building an algorithm to fit your design. I know I was talking to Hans about this. He was working on a scheduling problem. So you have to build some sort of genetic expression that will map into an actual individual, and that will be different for each domain. And you have to build a fitness function that creates a fitness, and that will be different for each domain. But as far as like the algorithm and the guts that run it itself, you can essentially build like a templated genetic algorithm that will run on whatever individual you supply it with, as long as you've given that requirement. And I know there's libraries out there that will do that. Is there any other questions? Okay, well, I appreciate you guys listening today and hope you found it interesting. If you have any more questions about this, please reach out to me. It's a favorite topic of mine. So I hope you guys have a great day.